Okay, it's great time to resume. It's Renzo Cavalieri, Tropicalization of psi classic.
Thank you, Paolo. Thanks, everybody. It's great to be here. Great to see a lot of familiar faces and a lot of unfamiliar faces. We will all be friends by the end of the week. I am here to talk about some joint work with A.Gross, which you can find in the archive. It just came out in December. And because this is a conference on enumerative geometry, I don't have to give my usual warm-up slide with moduli space of Mickey Mouses to motivate enumerative geometry being translated into intersection theory of moduli spaces, right? We're all familiar with the fact that this will be a talk about intersection theory of moduli spaces. But because every one of us has their favorite family of moduli spaces, not necessarily the same as mine, I'll just spend a couple warm-up slides to talk about the moduli spaces that I want to talk about today, which are moduli spaces, right? So these are infinitely many moduli spaces depending on two parameters, G and N, right? G means genus and N number of mark points, right? And the objects that are parameterized by these moduli spaces, the closed points, if you want, are stable curves of genus G with N mark points, right? So these are, almost Riemann surfaces, but they're allowed to have nodal singularities. They have to have finally many automorphisms, and we pluck out N smooth points, right? And if you want to be a little bit more fancy, it's a functor for flat families of stable curves with S sections, but who cares, right? I want to look at the perspective of this space as a space that allows us to do combinatorial algebraic geometry. And so in particular, it's a stratified space. And it comes with a bunch of tautological morphisms, right? So stratified space means that we can put an equivalence class on the objects parameterized simply by saying two objects are equivalent if they're topologically equivalent, they're homeomorphic as pointed curves, right? And then this cuts out the moduli space into locally closed subsets, right? That create a boundary structure, and the boundary is particularly nice, which is sort of like the technical term is normal crossings. If you zoom around it locally analytically around any point of the boundary, it looks like some coordinate axis, but locally analytically. Okay, and the tautological morphism, I usually like to say that these moduli spaces are not grumpy, but they're very sociable. They interact with each other. There's not just one MGN that doesn't talk to all the others, but they talk to each other in what way? Well, first of all, the strata are themselves made from moduli spaces. The strata are images of morphism from other moduli spaces, right? So for example, if we look at this particular, so my running example will be M bar 1, 2, genus 1 curves with 2 mark points. It's a two-dimensional space with this various strata. So let's look in particular this one orange point correspond to the calamari curve right here, right? It consists of a rational curve with 2 mark points attached to the node with another sort of rational curves with 2 points glued to each other. And this point, I can think of it as the image of a gluing morphism from product space of M bar 03 cross M bar 03. In other words, you give me one rational curve with 3 mark points, label 1 to an A, another one with other 3 mark points, labeled B plus and minus. And then what you do is you glue A with B and plus with minus, you obtain the calamari. Okay. So one way in which moduli spaces talk to each other is the strata are made from this gluing morphism. Another way is you can forget mark points, right? If I start from a genus 1 curve with 2 mark points, and I forget the point label 2, I end up with a genus 1 curve with 1 mark point. So I get a natural morphism from M bar 1, 2 to M bar 1, 1. And I have also sections going up, which says, okay, if I have a mark curve with 1 mark point, I can look above it at the marked 2 curve where the 2 mark points coincide. By that meaning, they lie on a rational component with only 3 points, right? And so this describes a stratum in particular, which is isomorphic to the moduli space. Okay? Now, I went a little bit fast because I have a lot of ground to cover. If you're already familiar, this was like old music. Otherwise, what I want you to take away is there's a bunch of rich combinatorics going on in here. What I want to talk about is these objects called psi classes. These are codimension 1 Chow classes in the Chow ring of the moduli space of curves, and they're constructed as the first Chen class of a line bundle in the moduli space. And this line bundle, which is called the ith relative cotangent line bundle, is built out of the geometry of the families of curves, right? In other words, if I have a family of stable curves with a section, I can look at every point of this section at the cotangent line to the fiber. And because I have a family, this cotangent line actually assembles itself to give me sort of a global object, which is a line bundle supported on the section, which then I can think of it as a line bundle on the base. And again, if I do this for every possible family of curves, this defines a line bundle in the stack. This cotangent line bundle, its first term class is the psi class. Okay, another way to think about this line bundle, which will be relevant in this talk, is, well, if I'm cotangent to the fiber, I'm also co-normal to the section. Right? So this cotangent line bundle can also be described as the co-normal to the section. So these psi classes, you say, well, why do you care? Well, first of all, I want to do intersection theory in this moduli space, and this is about as natural a class as it can get after the boundary strata, perhaps. But they're very interesting in that they do control the intersection of non-transverse strata. In other words, the Euler classes of the normal bundle to boundary divisors are expressed in terms of this kind of classes. And so anytime, even if you said, well, I'm a pure combinatorialist, I only want to do intersection of strata, because those are things that come from Picard. Well, you'll have to deal with psi classes, right? And the other thing is that they have very interesting and very combinatorial intersection structure, in the sense that if you take all intersection number of psi classes, means take all possible monomials that define a zero-dimensional cycle in MGN bar for all G and all N, and create, and then you get a bunch of numbers, infinitely number, put them in a generating function, and then Witten's conjecture conservation theorem says, well, this generating function is a tau function for the KDV hierarchy. Okay, if I have time at the end, I'll give my little bitchy comment on this, but what this means is that there's a lot of combinatorial structure to this intersection theory. It's the physicists hijacking our field. Okay. I did the bitchy comment anyway. And I'm being recorded, so I'm doomed. I'll never be invited to the physicist conferences. Anyway, now sidestep, I want to talk about tropical intersection theory in the moduli space of curves, on the moduli space of tropical curves. So let me give again the one slide about tropical geometry from infinitely far away. So tropical geometry is a combinatorial geometry of piecewise linear objects and functions. And it encodes some algebraic information about the generation of algebraic variety, right? And when one wants to do sort of a correspondence problem, to sort of try to extract some algebraic information from geometry, the game is exactly this. You have to try to decrypt algebraic information from the combinatorial objects. And also you have to understand what algebraic information is retained. So it's a two-step process. One, what is still there and what is lost, and what's there might be camouflaged by combinatorics, but you have to find a way to extract it. So in particular, tropical curves are just going to be one-dimensional tropical objects, and so graphs. These are graphs, but on top of just being graphs, I'm going to put a metric, which is each compact edge is going to have a length, and I'm going to put genus at vertices. And again, if you're familiar with stable curves, you see, oh, that kind of looks like the dual graph of a stable curve. That's not coincidence. Okay, and in fact, a tropical curve might arise as a tropicalization of a family of curves. And what this means is, and a little bit roughly, but I think morally correctly, is that if you have a sort of a family of curves on a small disk, or maybe an infinitesimal disk, a speck of a Artinian ring or something, right? Or a DVR or something, I don't know, or any algebra. So, and this central fiber is a stable curve, right? And so it might have nodes, it has multiple components, and these nodes have a local analytic equation, which is x times y equals something that should vanish at 0 and not vanish when you're not 0. Then what you can do is you can associate to this the dual graph of the central fiber, and the length of this edge becomes the power of the base parameter that controls how quickly or how slowly the node is forming. And so somehow the metric information in tropical curve is telling you not only that the curve is degenerating, but how fast it's degenerating. Great. So we have some connection to algebraic geometry, but let's step back into combinatorics again. If we want to do moduli spaces, then we should fix discrete invariants like a G and an N, and we should ask ourselves, what are all tropical curves of genus G with n marked points? And what ends up happening is that while you have a bunch of graphs, each graph has a certain number of compact edges. These compact edges get positive real numbers as lengths. So each different kind of combinatorial type of graphs can have an orthant worth of different metrization of edges, right? So an MGN trop, which again, I'm going to illustrate just in my running example of G equals 1 and X equals 2, is what's called a generalized cone complex. You get a bunch of cones and you glue them along faces. And sometimes you also have some sort of automorphism or self-gluing. You can fold a cone, or you can create like an ice cream cone like we saw earlier, and so on and so forth, right? So for example, right, in the case of N12 bar, I have a tropical modular space M12 trop that has 1, 2, 3, 4, 5 cones, right? And one of the two two-dimensional cones, and one of them is folded. And so often M12 trop is drawn as this picture right here. And at this point, I just want to point out, that there is a natural correspondence with the algebraic stratification, in that this cone complex is essentially the boundary complex of the stratified algebraic moduli space. Okay, questions, comments so far? Yes?
What's the folding about?
The folding is because, I'm maybe going a little too fast, but so this cone parameterizes this kind of graphs corresponding to two edges and two marked ends, 1 and 2 that have infinite lengths, and two compact edges with like X and Y, right? And there's a symmetry, right? You can sort of flip the two edges of the graph, and the graph with X on top and Y on the bottom will be isomorphic to the one with Y on top and X on the bottom, right? So you get a self map from this cone that identifies, say, the graph with edge lengths 2, 1 with the graph with edge lengths 1, 2, and so you quotient out like this self map. Yeah.
Do you end up with rigidity conditions too because of the lengths on the edges?
Rigidity condition, what do you mean by rigidity?
If you have a tensegrity thing, if you have certain lengths, you sort of, doesn't flex.
Oh, at this point, no. No, these are graphs that are not required to be planar, they're abstract, right? So at this point, no. Obviously you can start from here and construct all sort of other interesting things like modular space of maps into something, and then these things arise. But right now, this is sort of the combinatorial idea of an abstract curve, right? So there is no, yeah. Cool. So I want to give a little bit of, sorry, before I say this, I should say, and my other cheeky tagline for this talk, which is people that have been following kind of tropical intersection theory of tropical moduli space of curves, they expect the following, right? In genus 0, everything works. And in higher genus, everything doesn't work, right? Everything fails miserably, crashes and burns, right? And so let me give a short review of a short, but still not so short, and yet incomplete review of the genus 0 history, right? At the beginning of the millennium, right, Belair, Holmes, and Wachman studied moduli space of phylogenetic trees, which are these combinatorial objects coming from math biology or biology, I don't know, that then a few years later got interpreted by Speyer and Sturmfeld as the tropical Grassmannian. 2 or 3 years after that, Mikhalkin said, okay, this is really a tropical version of M0N, of M0N. The same year, Tabalev introduced his theory of tropicalization of subvariety of tori, and further took this kind of insight of Mikhalkin and framed it into this theory. A couple years later, Mikhail Kerber and Markwig introduced tropical psi classes in genus 0 and showed that the intersection number of tropical psi classes agreed with the intersection number of classical psi classes. And 3 years later, in 2012, there he is. He basically gave a conceptual understanding of this correspondence, whereas Kerber-Markwig, they just computed it combinatorially and said, look, the two things match. Eric said, well, this actually follows from the Fulton-Sturfeld's intersection. This is genus 0, and I'm pretty sure this is an incomplete account, but there's a lot of stuff by 2012. In higher genus, we start having anything at all in 2015 with Abramovich, Caporazzo, and Sam Payne that gave the first sort of tropicalization statement. Okay, so maybe I should say something. Before that, certainly was understood that there was this bijection between, this kind of poset isomorphism between the boundary complex of MGN bar and the tropical modular space. That's always, not always been known, but that was known before. But it was not before 2015 that there was any sort of connection with some kind of geometry, right? And so the first tropicalization statement was theirs, where they said, okay, really the way that you should think about the tropical moduli space is this skeleton of the Berkovich analytification of the algebraic moduli space, whatever that means. Right. A couple years later, myself with Melody Chan and Martin Lourdes and Jonathan Wise, we sort of promoted kind of this tropicalization statement to sort of a stack statement. We said, okay, this tropical moduli space, if you enhance it and you make it into some sort of functor over families of tropical curves, over some category of complexes, a moduli stack, and you recover some things such as the universal family is MGN+1 tropic. 5 years later, which is only 2 years ago, with Andreas Gross and Markwig, we developed a combinatorial theory of tropical psi classes in arbitrary genus. And a month and a half ago, with Andreas, we were able to say, okay, this combinatorial theory is a tropicalization. So again, I feel like I'm running like a marathon and a sprint at the same time, right? But the point is, higher genus is a lot more recent, it's a lot more complicated, but hopefully I'm trying to convince you it's not completely hopeless, even though certainly the reach is not hopeless. But let me spend one more slide to kind of explain why everything works in genus 0. The reason that everything works in genus 0 is that the moduli space M bar 0n is what's called a tropical compactification. And what does that mean? So start from the interior of this moduli space, M0, moduli space of PGL2 isomorphism classes of n distinct points on a P1, on a sphere. very simple object. This admits an embedding into a torus. This embedding into a torus can be tropicalized to give a fan inside the vector space of the co-characters of the torus. And this fan produces a toric variety that partially compactifies this torus. And if you close M0n this toric variety, you get M bar 0n. This is, again, the distillate of what it means to be a tropical compactification. But what do we get from this construction? Well, the first thing that we get is that the characters of the torus give a class of global linear functions on M0n trop that then can be used to define an embedding into a vector space. And in particular, this allows the integral lattice. So every cone comes with an integral lattice corresponding to the tropical curves such that all edges have integral lengths. And you know that these cones are going to glue respecting these lattices. Sorry. But we do not know in principle how the integral lattices of two adjacent cones talk to each other. And this global embedding in a vector space given by the linear functions coming from the characters of the torus allow us to relate. And then once you have that, then you really, like Eric's insight was that you show that the tropical intersection theory, this combinatorial process that I'm not describing here, but there is a combinatorial tropical intersection theory that agrees with the intersection theory of the toric variety they use to compare. Okay, so now let's step out of our comfort zone of genus 0. I'll try to slow myself down because now here's where the more complicated material or maybe the more novel material comes in. And I want to talk about the work with Hannah and Andreas from a couple of years ago, what went into defining tropical psi axes. So the first thing is we had to actually come up with a notion of family of tropical curves. And this is a map of tropical spaces, C to B, and here's an illustration. And what's a tropical space? A tropical space is some space which is locally modeled on a complex of rational polyhedra. But on top of that, it has what's called an affine structure, which is a sheaf, a subsheaf of the sheaf of piecewise linear integral function. So we want to kind of include this information of what functions are locally linear as part of the datum of what the tropical space is. And then, okay, a map of tropical spaces should be sort of a map that respects both the polyhedral structure and these affine functions. We want the fibers to be one-dimensional, to be tropical curves. So again, if we look at this example, right, my base is just a line. My family of tropical curves is the union of 4 two-dimensional cones, 1, 2, and these 2 that got folded into each other to be like ice cream cones. And the fibers at every point, if I look at the inverse image, I can see a tropical elliptic curve, right? A genus 1 curve with one infinite angle. The affine structures, it's not immediate to see from the picture, but it's somehow encoded in how I drew this picture, in the sense that I chose to draw these 2 flat cones as living inside an R2. And to do that, I bent this angle right here, right? So this is my pictorial convention to say, well, this line is a straight line, right? But if you think of this as an abstract cone complex, right? On this side, you do see a horizontal line. But on this other side, if you really take the sort of the generators of the integral lattice as basis vectors, then this line is not horizontal. Right? So something that if you just wrote, actually, let me draw this. If I wrote this cone on the right, just, as a cone, I would see a line like this. Right? But the information of this affine structure is saying this line with this slope actually makes a straight line with a horizontal line on the cone on the right. Right? So And then I have some technical conditions that maybe it's not particularly important to linger too much on, but there is some sort of short exact sequence that says that if you have affine function of the family are restricted to a fiber, you have affine of the fiber. And if you restrict to something constant, you are pulled back from the base. Get things that feel pretty normal, and that for a general point, I'm not telling you what general means, but the affine functions on a fiber are precisely the harmonic functions. Okay. Technicalities. But after you have the notion of family of tropical curves with affine structure, you can set up a moduli stack for these families. And this is well, it's not a nice stack, but it is a stack. It's not nice in the sense it does not have a finite atlas, finite cover by tropical spaces. But nonetheless, you can define a line bundle on a stack by defining it coherently on all families of tropical curves. And then you can define a tropical line bundle as some combinatorial analog combinatorial analog of the co-normal to the tropical section. And then you can define this tropical psi class operationally. Okay. Again, right? So there's a lot of technicalities that go into here, so I'm happy to talk more to people individually later, but let's just take it as, this can be done. Take some work, right? And so in particular, in the example earlier, if I think of this horizontal line of affinity as the first section, the first marked point in this family of curves, and I compute this tropical psi class against the fundamental class of this base, what this ends up detecting is sort of the change of slope that happens here, right? If I have a horizontal line that all of a sudden becomes slope A, then the psi class picks up precisely. Okay. So what we've done so far, and in our paper that we wrote with Han and Andreas, we did some computations to show that, for example, you can take the tropicalization of a pencil of cubics through 8 points to get a cover of M11 trop and compute the psi class that using our definitions, and you end up getting the same answer as an algebraic geometry. Psi class is 1/24, the class of a point for that. So what we had done at that point is sort of like, something that Hannah has built, her career on, which is like, look really carefully at an algebraic geometric problem and then say, well, this is the natural way to give a combinatorial construction that parallels it. And so what we've done is we've constructed a combinatorial theory that had the best hope, by this I mean Hannah's seal of approval, to be sensible, right? But we did not have any concrete way to connect it to algebraic geometry, right? And so that's the question that remained open after this paper. The paper already was 80 pages, so it's a good thing that we stopped it there, right? But the question that remained open is like, can we make sense of this combinatorial construction of tropical psi classes as some kind of tropicalization? And what had to be done, right? So this is sort of the content of this recent paper with Andreas. And what we had to do is, well, first of all, define a notion of tropicalization, which is more general than the classical torus-embedded localization a la Tebolev, but still contains information about affine structures. And then we had to tropicalize line bundles, tropicalize families of curves, and then understand what happened to this, what happens to the tropicalization of the connector. And so this is the plan for the next 20-25 minutes of my talk. Okay. So the starting point for us was saying, okay, if we have a toroidal scheme, then already from the 70s, Mumford, and I forgot the other two names, because I'm old. Yes, thank you. Knudsen and Sentinel, thank you, yes. They already associated.
Knudsen with a D, by the way.
Yeah. They associated a cone complex to a toroidal scheme, and this cone complex had an integral structure. So then once you have a cone complex, it's no big deal to maybe consider an extended cone complex. Allows so lengths to go to as well, right? So we could easily start from a toroidal complex and say, okay, we can get this combinatorial object, which is a collimate of cones with integral structure. And then we wanted to give a sheaf of affine functions. And the basic idea is, again, is to rely on the intuition that you get from toric varieties, where you say, okay, a Cartier divisor corresponds to a piecewise linear function, and an actual linear function, an affine function, is a principal divisor. That's the basic idea. Then there is a fair amount of like technical pain in when I said pain and then I look at Sam. But it was not meant to be.
That was his nickname in college.
This is like reminds me when I was a postdoc, very early postdoc, and I got invited to give a talk at UT Austin. I said keel over in front of Sean Keel, and then I also things happen. Anyway, there's technical work to be done to actually go from this intuition to like what is exactly the sheaf that you're constructing, because for a particular sort of open set in the cone complex, you have to throw away some strata and restrict things appropriately. It can be done. It's not something you want to see in a talk, right? But this is the basic idea. And so now we have a tropicalization that is sort of, well, that has some nice properties. The first thing is punctorial. You have a nice map of toroidal varieties that somehow respect the toroidal structure. You get an induced map of tropical spaces. It is invariant under log modifications, which means that if you, for example, blow up some strata or something like that, the actual tropical space does not change. Maybe it'll get subdivided, but the affine function not change. And that's actually very useful for us because, one could say, well, if you only restrict your attention to toroidal embeddings, you're never going to do family of curves, but it's okay. You can start with a family of curves, which is not toroidal, and you can blow up a bunch of things and get it to be toroidal, and the tropical object you get that, the affine structure doesn't notice. And then another nice property is that tropical cross ratios, which are these combinatorial functions that we define in our paper from 22, are actually the tropicalization in this sense of cross ratios. And so in particular, we give the 122nd proof that the tropicalization of M0n is M0n drawn. Okay, yeah.
What is a log scheme and what is a log modification?
Oh, I will tell you later. But for the 5 seconds thing, is a log scheme is a space with a nice divisorial boundary. Say, think boundary with normal crossings,
Okay.
right? And a log modification is do some birational transformation that respects this boundary. So for example, you can blow up a stratum, or blow up the proper transform of the stratum, or blow down a stratum, or stuff like that, right? But don't blow up a point outside a stratum, or stuff like that. Of course, it's, any log geometry in the audience will probably like say, oh, what are you saying? Okay, so then the next thing is we need to tropicalize line bundles. And again, here's a pretty picture with many colors and too much information. But the idea is the tropicalization line bundle from a combinatorial perspective is just the product of the tropicalization of the base by a tropical line. This often happens in tropical geometry, right? The combinatorics itself is a little bit trivial, but it gets an interesting affine structure. And so in particular, the tropicalization of a line bundle is a tropical line bundle, which is a torosaur over affine function on the base, if and only if the line bundle is a boundary line bundle. Can be expressed as the line bundle associated to some boundary class. Or equivalently associated to some piecewise linear function. And sorry, I should say one more thing. So the tropicalization line bundle is such a thing on the interior of the tropicalization. I carefully did not put a bar here. If you actually want to say when a tropicalization line bundle is a tropical line bundle on a neighborhood of a face of infinity, then you're asking something a little bit stronger, which is you still want to be boundary, but you want to be able to sort of be boundary within the orbit, the closure of the orbit, the stratum corresponding to that cone, right? So you still want to be, let me actually instead of trying to say generally, that it will confuse me and you as well. If I have a line bundle on this face, and I want to ask myself, when is it a tropical, when is its tropicalization a tropical line bundle in the neighborhood of this face as infinity that corresponds to this divisor? Then I want to be able to express the restriction of this line bundle to this divisor as, you know, a linear combination of the other divisor restricted to dt. In other words, I want it to be boundary in the orbit, in the blue. Okay. And one can like think about, okay, can one describe this condition in a purely combinatorial way? And the answer is yes. The combinatorial description is something that we call in our paper being combinatorially principal. And you can do it if and only if you have an affine function on a neighborhood of the cone corresponding to tau that corresponds such that its restriction is equal to the piecewise linear function phi that defines your line bundle. Okay, so you start with a boundary line bundle. You say, okay, but the support of this boundary divisor contains the face. But if I can use an affine function to eliminate the face from the support, I can sort of transversalize with respect to that. And so we get this combinatorial condition. And so finally, with all this set up, oh, no, not finally. That's one more slide before finaling. Tropicalization of families of curves. Well, first of all, we have defined this functorial tropicalization. So given a family of curve, we do get a corresponding map of tropical spaces. This is almost a family of tropical curves in the sense of our previous paper. In the sense that, again, the content of this point 2 is that we have enough affine functions to satisfy all the axioms that define a family of tropical curves for a generic point. In a sense, if a point is genus 0, or it's at least if it's on an edge, if it's a genus 0 or if there's an edge adjacent to genus 0. Sorry, if it's genus 0 and more than 2 valent, or it's genus 0 2 valent, but on an edge adjacent to genus 0. But then one thing that we realize is if we really want to talk about psi classes, we don't necessarily need to have this tropicalization of this family of tropical curve necessarily be a family of tropical curves everywhere. What really matters is that we have enough affine function to make the tropical family of tropical curves in a neighborhood of the section that we want to go explore for the psi class, right? And remember, the psi class, we're defining it somehow as sort of the first term class of the conormal bundle of the sections. It really cares about infinitesimal information on the section. Right? And so the way, again, that this is detected is you have to sort of we define a torsor, a torsor over the affine functions on the tropical space that we call Fc of Si, whose sections are piecewise linear functions that are affine in a neighborhood of the section minus the section, and they go to infinity towards the section with slope 1. So these are sort of, again, very similar to the idea of saying, when I talk about the section of O of D, these are rational functions that have a pole. And so that's the same. And then we can prove that this affine torsor is the tropicalization of the conormal bundle of the section, if and only if the piecewise linear function that goes to infinity with slope 1 in the section is combinatorially polyhedral on the corresponding cone at infinity corresponding to this section, the dual to the thing. So there is again a combinatorial description of what it means for this affine torsor to be the tropicalization of the corresponding. But now finally, we put everything in place to have the theorem that says, okay, when this condition holds, when this particular piece of linear function is combinatorial polyhedral, then the tropical psi class of our previous paper is indeed the tropicalization of the psi class. And so at this point, if you can verify this condition, you get that sort of correspondence theorem come for free. They're no longer something that you have to check and say, wow, it worked. Amazing, right? But this kind of. And somehow again, it's a lot. I've thrown at you a lot of technicalities very fast. But the paraphrasis, what I want to be the message of this talk is that, well, this technical condition means that tropical geometry is not always able to see the algebraic information of psi classes. Somehow it only sees it if you're considering families that degenerate enough near the section. But if it does, then it sees exactly the tropical psi classes that were defined a couple of years ago. And this is the end, so thank you.
Yeah, is there some, when you're defining these tropical psi classes, it feels like you're defining some kind of map to an Arden stack and pulling them back by that. There's some world in which this makes sense.
I mean, yes. I mean, in the sense that you're kind of there is sort of like a very precise relationship between this moduli space and tropical curves and sort of the Artin fan of energy bar, and so you could probably express some of that language. Yeah, I don't think that I have thought too hard about it, but I would guess that, yeah.
What's a tropical cross ratio?
So a tropical cross ratio is just a. Let me see what's the most efficient way. So it's a combinatorial way to describe a way to get a function from a family of tropical curves to R, right? And the way you do it is somehow you have to sort of pick a subgraph of a tropical curve, which is of genus 0, and with at least 4 ends that you can distinguish, right? And then you should be able to this subgraph, as you follow it along, your family might further degenerate, but if in the least degenerate stratum is already genus 0 and has at least 4 ends, it cannot, it can only get more. Can break more, it cannot, lose that information. And so that gives you sort of like a map to M04 trop, which is a tripod inside R2. And then you can sort of compose with any sort of projection you want to R, like vertical, horizontal, or anything about R. And then you get a map to R. This is one way to describe it. Another way, which is more elementary, is to say, you pick these these two pairs of edges in these subgraphs. They define, because this is a genus 0, they define two paths. And you look at the sign the sign length of the intersection of these two paths. And that's a number. And now you do it for every fiber. That's exactly the same function. Yeah.
Could you say a word about how these matroid psi classes of Dusty Ross and Tissue are fitted to the story?
I can't. No. This is something I should look up, but I haven't yet. I hope they do tie up.
Is there any way of like, so there's some sense there's these psi classes that are seeing degenerations of lengths of edges in your dual graph, and then there's some sense in which the psi classes correspond to weird things happening internally in your moduli space. Is there any way of correcting the tropical psi classes and making them closer to the algebraic geometric psi classes?
So this is actually funny that you're asking this question, because I have a grad student that I've asked him to do this in genus 1, right? And so what so let me say something philosophically like that, right? So tropical geometry is not always able to see everything that algebraic geometry has. But sometimes we create correspondence theorem by saying this is the minimal amount of geometric information that we need to feed tropical geometry. And after that, if you feed tropical geometry, this initial geometric information, everything else can be reconstructed this way. Right? So I'm kind of taking your question as like, can this be done? And the answer is, I mean, it should be doable in the sense that, so what I said earlier is this moduli space of tropical curves as a moduli stack of families of affine curves. So these things where we can do intersection theory. The problem is, as a purely combinatorial object, it contains certainly sort of family of tropical curves that do not come from algebraic geometry. And in fact, the stack does not have a finite atlas, but what one could try to do is to actually artificially use algebraic geometry to say, let's construct a finite atlas that will define exactly the information that is needed. Now, I think that in genus 1, this should be like a reasonably high chances of success thing, because we know that essentially like the only one non-boundary information in the tautological intersection theory in genus 1 is psi1 and M11, right? And somehow it should be possible to very carefully just feed that, create an atlas for M11 trop, and then get sort of atlases everywhere else just by pull back and show that everything is reconstructed. For every other genus, there's only sort of finite amount of information that you need to then be able to reconstruct everything from string and dilaton, which are two things that, again, tropical intersection theory can see. Right? And so in principle, it should be that doable. Obviously, it gets progressively more complicated. So if my grad student does genus 1 quickly, then I'll make him suffer more. But yeah.
What are the prospects of giving a tropical proof Newton's conjecture?
Well, I mean, that's my holy grail, right? In a sense, sort of like I mean, at this point, they're still very slim, right? But somehow, I don't know if necessarily Newton's conjecture is the one and only holy grail, but there's a lot of when I was joking earlier, like the physicists like are stealing our thunder, right? There's a lot of things about reconstructions of cohomological field theories and stuff, but Newton's conjecture as well, right? Where the proofs that we have come from an intuition that has nothing to do with the combinatorics, right? And so my hope is that by trying to understand better and better this combinatorial aspect of the intersection theory, we might be able to, for example, say where does an R matrix that reconstructs a co-FT come from? That is still a lofty goal, but is a little less lofty than Witten's conjecture. But yeah, if one just wants to dream, then yes, I would love to like find a proof of Witten's conjecture that is really saying this is a combinatorial phenomenon. It doesn't need bosons and fermions and whatever.
Okay. There are no more questions. Let's thank Renzo again.